Ready to start Unit 5, and our objective in this first section, 5.1, is I can review solving systems of linear equations. So hopefully this video will be a complete review, but it'll go over some important things that we're going to need as we progress in this unit. So let's look at our warm-up first. Let's go ahead, and it says solve for y. So we know to isolate any variable, we want to do any adding or subtracting first. So in this first one, I definitely would like to add that 6x to help eliminate and just solve for this y. Now we do usually put our variables before our constants. That puts it in that nice slope-intercept form when it's a linear function anyway. Okay, problem 2, similar idea. My y value, in order to isolate it, I want to add my 3x over to both sides. That's going to leave me with a negative 2y. And again, I'm going to put that x term first. And then we need to divide by negative 2, and everything gets divided by negative 2, the 3x and the negative 4. And I'm going to go ahead and put my negative up with my numerator when I have a negative 3/2 x. And then I'll change my negative 4 to a positive 2 when we divide. Okay, let's look at the last one, number 3. We have all of our variables on the same side, and our constant also is on the same side. So I'm going to think about subtracting both my 9x and my 12 over to the other side. I'm just, however, going to write that 12y first and put my 9x that I've subtracted over and my 12 that I've subtracted over. And then everything needs to be divided by 12. Well, 9 divided by 12, each of those are divisible by 3, so that's going to leave me with a negative 3/4 x, and negative 12 divided by 12 is a negative 1. So this idea and the skill of solving for an indicated variable we're going to need today is as part of what we're going to do to solve systems. So let's go ahead and look below the warm-up. It says, recall solving systems of equations in secondary 1. So we did this last year. You also did it in 8th grade. Remember, we're looking for an intersection. When we solve a system of equations, we're looking for an intersection of two lines. And there's 3 different ways that we're going to do this. We're going to graph. We're going to do substitution. Whoops, that's a spell check. Substitution, and we're going to do elimination. So when we're solving a system, we're going to look for points of intersection. And there's 3 different possibilities. We could get a problem that has one point, one solution where they intersect. We could have it where they intersect everywhere and have infinitely many solutions, or they could never intersect, and we'd say that there's no solutions there. So let's look at example 1, which is graphing. So example 1 says to solve the system by graphing. So the first thing I want to do in any problem that involves graphing lines would be to put it in slope-intercept form. So I'm going to think about this first equation, finding my y, and I notice that my coefficient is 1/2, and I would prefer to just get rid of that fraction right now. So I'm going to multiply that whole equation by 2. I'm going to put it down here where there's a little more room. So if I do 2 times 3/4, that really gives me, 6 over 4, which simplifies to 3 over 2. And then 2 times 2 is 4, and 2 times 1/2 is just a 1y, which is really nice when I'm solving for y. So the only thing I have to do is subtract my 4, and I'd have my y that's isolated. So y is going to be equal to 3/2 x minus 4. So there's my first equation that I need to graph. And then my second one, which I'm going to just draw an arrow down here, I'm going to start by adding that 3x over. So I end up with a negative 2y that stays. I've added my 3x, and I still have a minus 4. Now everything can be divided by negative 2. So negative 3 over 2x, and then plus 2. So there's our second equation. So let's graph both of these and find their solution. So remember, when graphing a linear equation, we want to start with the intercept, which is that constant. So I'm going to start with negative 4, and I'm going to count my slope, rise over run. So up 3 and right 2, because they're both positive. Up 3 right 2. I tend to count my slope, especially on the first line, as many times as I can, because I know that I'm looking for an intersection. So I'd like to just get that one done really nice first, and as soon as I find the intersection in my next line, I know I'm finished. So the best that I can, draw a straight line connecting those points. And let's do a similar thing for our other line. Our intercept is at a positive 2 this time, but slope is negative 3 over 2. So down 3 and right 2, and there we have our intersection. I'm going to count it one more time. Down 3 over 2. And really, once you have the intersection, you don't have to count any more points unless you just want to make it a super nice graph, which is not a bad idea. And remember, we're looking for that intersection. So that's what we're looking for, and that solution is always an ordered pair. So that point 2, negative 1 is the solution to this system. It's where they intersect. Let's try it, a next method, example 2, using substitution. So substitution we've done several times. Substitution means taking something out and putting something equal in its place. So a lot of times people will look for an equation that they can solve for either x or y. So as we look at example A, I'm seeing my second equation. I have a y that I can solve for. So I'm going to think about solving just that little equation for y. So I would just need to add the 6x over with that negative 10. And now I can take all of that I say that y is now equal to, and I substitute it into the other equation and replace that y. So I'm going to rewrite here. I have negative 2x plus 2 times, and as I substitute, I'm going to use parentheses. I'm going to substitute in this whole 6x minus 10. So before we can solve, we've definitely got to distribute our 2. So we still have a negative 2x, but plus, so we'd have 12x, and then we'd have minus 20. Combining like terms, we end up with 10x. I'm going to go ahead and add my 20 over, which also gives me a positive 10. And when I divide by 10, I get that the x value is 1. Now, this is not my final answer because I know my final answer is an ordered pair, and this is just going to be part of it. So I need to still find my y. I can plug this x value into either of the original equations, or I can plug it into this second equation that I manipulated to solve for y. And I think that that's the better choice because I'm solving for y. It's already isolated for me. So I substitute in my x value of 1, and we'd end up with 6 minus 10, which is a negative 4. So that gets us the rest of our answer. We just want to put it in a nice ordered pair because remember, graphically, we're saying this is where those 2 points intersect. These 2 points, when plugged back into these equations, make both of them true. Okay, let's try it again on B. So again, for substitution, choose a variable, x or y, that you could isolate. I kind of am drawn to this first one again because the y is already alone, doesn't have a coefficient. All I need to do is subtract that 3x, and then I'm ready to do some substitution. So I'm going to take what I say that y is now equal to, and I'm going to substitute it into my other equation and replace that y. So 6x plus 2 times y, which I'm replacing with a negative 3x plus 7, is equal to 5. So again, we've got to do some distribution. Let's see, that gives us a negative 6x, but a positive 14 as we distribute. Ooh, interesting. Look at both of my x terms. They're the same term, but our variables, their signs are the opposite, which means that they've eliminated, they've subtracted each other out, and we're left with this statement, which definitely 14 does not equal 5. So remember, when our variables eliminate each other, we look at what's left and we look and see, is this a true statement or is this a false statement? And this is definitely false. And because it's false, that means that there is no solution. these lines are never going to intersect. There is no point that they have that's exactly the same, which probably means that they are parallel. Parallel lines never intersect. All right, let's try our last method, elimination. Now, elimination gets its name because we want to eliminate either the x or the y variable, and you can choose which either one that you want to. Some people have a preference and they like to eliminate x's or they like to eliminate y's. Hopefully you can find a pattern that you like. You can look at the numbers and try and decide. For instance, maybe I'm looking at this going, well, 7 and 9 are kind of big, but 7 and 4 on the y's are maybe a little bit smaller. So maybe I want to eliminate those. Well, in order to eliminate those, I need to be able to add them together, and it gives me a 0. Well, right now, this would give me, an 11y? So I need to be able to make them the same coefficient, but they have to have the opposite signs, and then they eliminate. So I'm going to multiply this first equation by a 4. And I'm going to multiply this second equation by a 7. Now, remember, I'm trying to eliminate the y's. So if I'm multiplying by a 4, that gives me 28y. And if I multiply my second one by a 7, that also gives me 28y. But right now, they're both positive. And in order to eliminate, one of them needs to be negative. So I'm going to say, let's make that 7 on the second one a negative. So that would give me a negative 28 as I distribute those. So everything in this equation needs to be multiplied by this 4 or the negative 7. So I'm going to start with my first equation, and I'm going to distribute that 4 to each term in that equation. So I end up with 28x plus 28y equals, I know it's going to be negative 4 times 28. Well, 1 times 4 is 4. 2 times 4 is 8, so negative 84. And then in my second equation, again, I'm distributing negative 7 times negative 9, so that's going to be a positive 63x. Negative 7 times 4, so there's that negative 28 that I needed, equals negative 7 times 14, so let's see, negative 98. So I wanted to eliminate the y's, and now I can. When I'm adding these two together, 28y and a negative 28y are opposites, and they're going to give us 0. So when I add what's left, 28 plus 63, so we end up with 91x, equals negative 84 plus negative 89, or 98, excuse me. So let's see, negative 182. And then I have to divide, which I do not have this one memorized. So negative 182 divided by 91 gives us a nice negative 2. So I now know my x value, which again is not my final answer because I want to write that as an ordered pair. So now I need to substitute back in to find my y, and I can substitute it back into either of the original equations, whichever one feels more comfortable to you for a reason. If it feels easier, it has less negatives, whatever your reason is, it doesn't matter which one you plug it back into. I'm going to plug it back into this second one. So negative 9 times x. Well, I now know my x is negative 2 plus 4y equals 14. So I have 18 plus 4y. So I'm trying to solve for y. So I'm going to subtract my 18. 14 minus 18 is negative 4. And dividing by 4 gives me a y value of negative 1. So my final answer, written as an ordered pair, these two would intersect at the point negative 2, negative 1. So in elimination, we want to eliminate one of the variables. So in problem B, I want to think about this one maybe a little bit different. Sometimes, instead of making equations bigger, we can make them smaller, those coefficients and constants smaller to help us maybe eliminate. So for instance, looking at some of these numbers, maybe they're a little bit big and you're thinking, God, I wish they were a little bit smaller. Well, I notice that 15, 27, and 3 are all divisible by 3. And 25, 45, and 5 are all divisible by 5. So not every equation will this work with, but some it may, so you may want to think about it. What if I think about dividing by 3, which we can say multiplying by 1/3, on that first equation, and let's divide by 5 or multiply by 1/5 on that second equation. So that's going to give me, again, I'm distributing this to each term as I think about simplifying this equation. If I take a third of -15, I get -5x. A third of 27 is 3. Whoops, it's 9, excuse me, 9. And a third of -3 is -1. So those are much more manageable numbers. Let's take the second one. We're taking a fifth. So 25 divided by 5, 45 divided by 5, and 5 divided by 5. So in this case, this worked out really nice for me. Dividing by those GCFs that I saw in common, I now am ready to eliminate because I have -5x and +5x. Those eliminate each other. A +9y and a -9y. Those eliminate each other. And I also have a -1 and a +1, which also eliminate each other. So here's where you have to be careful. Back up here on the last example set, problem B, we ended up having our variables subtract out, which is exactly what's happened here. Our variables have eliminated each other, which means we look to our constants to see what's left, and there's also a 0. So remember, we're looking for something to be true or false, and in this case, what we're left with is true. 0 does equal 0, which means that there are infinitely many solutions here. When we're looking for where these lines cross, there are infinitely many points that this happens at, which means those two lines are the exact same line. They would land right on top of each other if we graphed them. So that was kind of a quick review. Go ahead and self-assess. How do you feel about solving these systems of linear equations? And good luck on your assignment.